Hello and welcome to the AS Chemistry lecture series. Today we're going to start chapter 6, which is on enthalpy changes. Now this is the first time we're going to talk about energy changes beyond something like ionization energy. And we're going to go and delve deeply into not just how much energy something requires, but how we think and look at energy when it comes to chemical reactions and physical processes. In this chapter, in the enthalpy change chapter 6, we're going to start by talking about what is an enthalpy change, what exactly does that word mean, how do we show it in graphical format. Then we're going to look at standard enthalpy changes. There are a lot of definitions we're going to see in section 2. And then we're going to move more into the mathematics of enthalpy, into measuring the enthalpy changes and Hess's law, bond energies and what that means, and calculating enthalpy changes using bond and energy. So we're going to go through 6 different sections, as well as one practical exam, which is a calorimetry practical. So let's get started with section 1. So what exactly is enthalpy and what is an enthalpy change? So in this section, we're going to delve into the definition of enthalpy and how we think about energy exchanges in chemistry. First of all, before we start talking about energy, we need to define the conversation. We need to define how we talk about energy, because energy can be a tricky subject, especially when it comes to the mathematics and the science, positives and negatives. And that's because we can think of chemistry or energy as happening with 2 different things: the system and the surroundings. The system is classified as the chemicals participating in the reaction, mainly the reactants. Sometimes it might include the products if it's an equilibrium reaction, which we'll talk about later, but it's usually mainly the reactants. So the system is the thing that we are studying, the thing that we care about. The surroundings, on the other hand, is everything around that. The surroundings is the area around the system, and it's not just limited to the area directly around the system. It's definitely things right around the system, like the solvent. The solvent is usually not part of the system, it's part of the surroundings. So if something's an aqueous solution, then that aqueous, that the water, is part of the surroundings, not the system. So for example, if we have a very basic chemical reaction, something along the lines of HCl aqueous reacting with NaOH aqueous, and then that giving us water and sodium chloride aqueous, what we will define as the system here, the system would be that HCl and the NaOH molecules. So the sodium hydroxide and hydrochloric acid are the system. However, these aqueous parts, let me use a different color. The aqueous in this equation, so the aqueous here, the aqueous here, is actually part of the surroundings. All of that water that the sodium hydroxide and HCl are floating in, that water, that aqueous water, is actually part of the surroundings, not the system. The system is only the chemicals that are actually reacting. The hydrochloric acid and the NaOH are reacting with each other. The water is simply there as a solvent and therefore is part of the surroundings. Other things that would also constitute parts of the surroundings are the air and the air around the reaction vessel. So both the air inside of the beaker or test tube where it's happening and the air around that system. The reaction vessel itself, so that beaker, that test tube, that Erlenmeyer flask, all of those things will be part of the surroundings. Any instrument in the reaction vessel, so if we had a thermometer in here, that will be part of the surroundings. If we had styrofoam cups surrounding this vessel, that will be part of the surroundings. Essentially anything that is not the actual chemicals reacting are part of the surroundings, not the system. Now, because of this idea of the system, right, we can have three different kinds of systems. The first is an open system. Now, an open system is very simply one where mass can leave the container that the reaction is happening in, and energy can come in and out of the container. So essentially think of like an open beaker, an open test tube. If we had a reaction and a gas was being created, that gas will be able to escape. Energy can go in and out of the reaction vessel. So both heat can go in and escape the reaction. So if the reaction is giving off heat, it can escape. We can have a closed system. A closed system is one where energy can go in and out, but matter cannot. Mass cannot escape. So if we grab the test tube and we put a cap on it, that will be a closed system, because energy can go in and out, heat can come in, heat can go out, but mass and matter cannot escape because of that cap. And finally, we can have an isolated system. An isolated system is one where neither energy nor matter nor mass can come in and out of the reaction vessel. Now, an isolated system, a perfectly isolated system, is impossible to achieve, but we can get very close to it by using insulation and insulating our system so that energy cannot come in and out. Or as little as possible energy can come in and out, really, should I say. So that's it for that kind of terminology, right? Having the idea that the system versus the surroundings, the system being the things reacting versus surroundings being everything else, including the solvent like water, and that's why it become very important in our conversations. And the fact that we have three different kinds of systems. One which is open, where matter and energy can be transferred. One which is closed, meaning only energy can be transferred. And one which is isolated, which means neither energy nor matter can be transferred. Now, because of this system versus surroundings idea, we can talk about the idea of an endothermic versus an exothermic reaction. Now, both a chemical reaction or a physical change like melting or boiling can either be exothermic or endothermic. And these are two opposite ends of the spectrum, which essentially relate to energy. Exothermic reactions are those in which heat is being released during the reaction. So heat is given off by the system. It's being released by the system, which means that the temperature of the surroundings rises. So think of something like burning a fuel or burning a pile of wood, for example, for a bonfire. The oxidation of carbohydrates in cellular respiration, which gives off energy. The reaction of baking soda and vinegar, which gives off heat. Anything that gives off heat is going to be exothermic. So a fire, being the most common example, is exothermic because a fire gives off heat. It raises the temperature of the surrounding area around it, and therefore it's exothermic in nature. Endothermic, as you can probably guess, is the exact opposite. Endothermic reactions are those in which heat energy is absorbed by the system, meaning the temperature of the surroundings goes down. So think of ice. Melting of ice, and this is the one which is a bit of a weird idea, the melting of ice is an endothermic physical process. Whereas burning something is chemical, melting of ice is a physical process that is endothermic. Now, why is it endothermic? The temperature of the surroundings is lowered. The ice itself is absorbing energy from those things around it, like your hand, if you were to hold it, to melt. That energy is going to weaken the intermolecular forces between the water molecules, the hydrogen bonding that we talked about in earlier chapters, and it's going to transition that ice into the liquid state. That process requires energy because we're breaking bonds or we're weakening intermolecular forces. And so it's an endothermic process. That's why it feels cold to us. It's absorbing energy from our hands. The decomposition of limestone is another process that's endothermic because it requires us to heat it up. dissolving ammonium salt in water, which is what happens in a cold pack that you use for sports injuries. And even photosynthesis is an endothermic process that absorbs energy in the form of ultraviolet light. But this idea of exothermic versus endothermic process is going to be at the very core of the conversations that we have in this chapter, because we need to discuss whether a process is going to be exothermic or endothermic in order to describe how energy is related to both a chemical and a physical process. Now, enthalpy change. The word enthalpy, which you're going to hear a lot in this chapter, is the main focus of the chapter. It's used to describe the total heat energy associated with the materials that react. So essentially, the word enthalpy is the same as saying heat energy. So those two things in your mind should basically be identical to each other. There are some nuances to it, but we're going to essentially think of enthalpy as heat energy. So more often than when, instead of talking about enthalpy by itself, we talk about what we call the enthalpy change, delta H. Delta in chemistry, the capital Greek letter delta, which is a triangle, means change in chemistry, and then H means enthalpy. So delta H means enthalpy change. We usually worry not about the just enthalpy of things, the heat energy of things, but we worry about the heat energy change, enthalpy change, of a process. So is the process giving off energy or is the process absorbing energy? The heat energy transfer during a chemical reaction or a physical process is what we call the enthalpy change, and it's usually measured in kilojoules per mole. Kilojoules is a unit of energy, and it's very important that you start to learn this because we're going to use this a lot. It's a unit of energy that we talked about before when we did in ionization energy. So kilojoules per mole means amount of energy per mole of something. Now, what is a something? That's going to change depending on the different enthalpy changes that we're going to discuss all throughout this chapter. So it's how many kilojoules of energy either absorbed or given off by a number of moles of something in the reaction or in the physical process. Now, we can associate different signs with both endothermic and exothermic processes, and this is something that is going to be one of the main sources of error when you do mathematics. You need to understand exactly what the sign on an enthalpy change means, because that logic, that understanding will allow you to double check your work when you're doing mathematics. Because if you have a process that you're told is exothermic, but you get the wrong sign in your answer, then you know you did something wrong. The enthalpy change during an exothermic reaction is always going to be negative, since the system itself is releasing energy. So delta H for an exothermic reaction, the enthalpy change for an exothermic reaction, is below zero or negative. And that's because the products have lower energy than the reactants. So during an exothermic reaction, one of the ways we can see this is that if we have the, we'll do this in pink. If we have the reactants yield the products, then in an exothermic reaction, because delta H is negative, because heat energy is given off, we can think of heat as a product. So the reactant gives off a product and heat, which means that the reactants have higher energy than the products which have lower energy. Where is that extra energy going? That extra energy is the heat that's being released. So we go from reactants that have a higher energy state to products that have a lower energy state. And because we're going from a higher energy to a lower energy, we produce heat, which is a form of energy. That's where the extra energy is going to. And so delta H is for an exothermic reaction is always going to be negative or below zero because we're giving off energy. The system is losing energy, and that's why it's negative. On the other hand, the enthalpy change during an endothermic reaction, and a reaction that absorbs energy, is positive since the system is gaining energy, it's absorbing energy. The products have a higher energy than the reactants, and so delta H is greater than zero or positive. So in an endothermic reaction, we have the reactants absorbing energy, so we're going to put heat as a reactant to produce some products. So essentially in an endothermic reaction, because the reactants are lower in energy than the products, in order for the reactants to become the products, they need to gain energy. And so the reactants are going to absorb energy in the form of heat and then become the products, which are higher in energy. That's why we say the delta H of our endothermic reaction is positive or greater than zero, because the reactants, the system, is absorbing energy in order to create a higher energy product. This idea of enthalpy changes lie at the center of this chapter. If we don't understand what enthalpy is, if we don't understand how enthalpy is given off or absorbed by a reaction, meaning exothermic is if it's given off, endothermic if it's being absorbed, then we won't understand the mathematics that come later on, the diagrams that are going to come later on, so on and so forth. So, how can we visually show this, right? Because we know we can show reactions in this manner. Reactants yield products, and I could use heat as either a reactant or a product to show an exothermic versus an endothermic reaction. But what is a graphical way in which I can show the reaction either being endothermic or exothermic? Well, these are called reaction pathway diagrams. The action pathway diagrams are something we can draw to show the energetics involved in a reaction. And what do we mean by energetics? We mean how highly or lowly energetic is a chemical reactant or a product. So are the reactants higher in potential energy than the products, or vice versa? And we do this by showing the difference in energy visually. It shows the relative enthalpies of the reactant and the products and the enthalpy change of a reaction as an arrow, and it might also include something called the activation energy. Now, the activation energy is the minimum energy colliding particles have to have in order to break bonds and start a chemical reaction. Whenever reactant particles collide with each other, they have to do so with enough force. So if I have a reactant particle here, and another reactant particle here, and they're traveling at a very, very slow rate, when they eventually collide with each other, instead of reacting with each other, if they're not moving fast enough, if they don't have enough energy, they're simply just going to bounce off each other. However, if I have two particles and they're moving much more quickly into each other, if they have much more kinetic energy and they collide with enough energy, what I'm going to get here is a reaction if they have enough energy, because they have succeeded in overcoming the activation energy. And then those two molecules might bond together and create a product molecule because they had enough energy to react. So activation energy means the amount of energy these molecules need to collide with in order to actually create a product, to create a reaction, instead of just simply bouncing off each other. Now, and the reaction pathway diagram is going to show all of this. It's going to show the relative energies of the reactants and the products. It's going to show the activation energy of the reaction and the enthalpy change of the reaction. Reaction pathway diagrams are also sometimes called energy level diagrams, which is the preferred term I use, energy level diagrams. And they're very useful in visualizing the changes in energy. However, they're not graphs, they're sketches. They show the relative changes in energy. They do not show actual exact numbers. And that's something that's very important. It's the idea of a sketch versus a graph. So let's talk about that for a second before we keep going with this topic. A sketch is a rough drawing. A sketch is a rough drawing that is used not to show exact numbers, but to show general trends and shapes. On the other hand, a graph, let me draw the dividing line here. A graph uses exact data. Meaning there are numbers associated with it that we have to graph and plot individually. It is used to do calculations and find data, or find actual data, meaning numbers. So we actually need to have numbers in order to make a graph. We can't make a graph if we don't have data that we need to graph. So something like a sketch might be, if I had to draw a sketch of, let's say, something that we've actually seen, the relationship between pressure and volume. I know that as volume increases, pressure goes down. So the sketch of a graph of pressure versus volume might look something like this. This is a sketch. Notice that I'm not plotting individual points. I'm just saying that as volume increases, pressure decreases and vice versa. On the other hand, if I wanted to do a graph of pressure versus volume, I would need pressure versus volume data. Meaning I will need to be able to see that as pressure goes up, volume goes down, and vice versa. So maybe this is 1. I know I'm going to keep it simple here, but 1, 2, 3, 4, and then the pressure will be 4, 3, 2, 1. So I will have to actually, in a graph, plot those individual points. So this is 1, 2, 3, 4, 1, 2, 3, 4. I'll have to have axis numbers. I'll have to have an axis label. So pressure versus volume, 1, 2, 3, 4. And then I'll have to actually plot this data. So if pressure is 4, volume is 1. So I'll have to plot the data point. If pressure is 3, volume is 2. And I'll have to actually plot this data: 2 pressure, 3 volume. 1 pressure, 4 volume. And then do a line of best fit. And part of my line of best fit, that's not the best line of best fit, but not exactly in the best position to be drawing here. But I will have to actually draw the line of best fit. So I have data that I'm actually plotting and graphing in a graph. Because then I could say, okay, if let's say, if I have pressure is equal to 2.5, then what is my volume? I could actually go in here and say, okay, if this is pressure, then my volume will be also 2.5. I would actually be able to use this data for graphics, for collection of data. I will be able to use this graph for collection of data. Where I cannot do that with a sketch. I couldn't tell you here, oh, if the pressure is 2.5, what is the volume? Because this is simply just a sketch that shows the volume pressure relationship, not an actual detailed graph. So this is something that's going to have to come in handy, because we're going to start seeing a lot of graphs and sketches both in the practical paper 3 exam and in paper 2 as we go into thermodynamics and enthalpy. So having a very clear idea of the difference of a sketch versus a graph is something that's going to serve you well as we go through everything that we're doing. So energy level diagrams are not a graph, they are a sketch. They show us general trends, general data, general shapes of things. All right, so let's go back to that. So a reaction pathway diagram or an energy level diagram is going to show us some general shapes. It's going to show us the difference between the reactants and the products in terms of energy. It's going to show us the enthalpy change of that reaction, and it might show us the activation energy. The diagram is going to show what we call what is the enthalpy in the y-axis, or the energy of the reactants and the products, and the reaction pathway in the x-axis. What does that mean? Because that's a very big x-axis, right? Reaction pathway just means reactants versus products and the stuff in between. What energy do the reactants have? What energy do the products have? And how do we get from point A to point B? And I'm going to show you a picture in the next slide that's going to make a lot more sense. The enthalpy change, or delta H of the reaction, is the vertical distance between the reactants and the products. And this is very simply because the energy difference between the reactants and the products is going to be how much energy is needed to be absorbed by the reactants if the products are higher in energy, or released by the reactants if the products are lower in energy. And then finally, the activation energy is the vertical distance from the reactants to the highest point in the diagram, because that's the energy that needs to be overcome for the reaction to happen. Now, this is all very good in terms of words, but let's look at an actual drawing to make more sense. This is a reaction pathway diagram or energy level diagram for an exothermic reaction. That's going to be important here. Now, let's start by remembering that an exothermic reaction means that the delta H is going to be negative. The delta H of this reaction is going to be negative in value, or lower than 0. And so why is that the case? This is the case because in an exothermic reaction, the reactants are higher in energy than the products. So here in this reaction, what we're looking at right now is a combustion reaction between methane, O2, and O2, which is methane and oxygen, to create carbon dioxide and water. So this is a combustion reaction of methane. It's what happens when we burn methane. Now, with the burning of methane, you'll notice that the methane and oxygen, the y-axis being enthalpy or energy, the methane and the oxygen are higher in energy as the reactants than the products, carbon dioxide and water. So in average, when methane burns, it's going to go from this level of energy to a lower level in energy for the products. All that energy difference has to be released. So the enthalpy change for this reaction is negative, because as the reactants, which are higher in energy, become the products, which are lower in energy, that extra energy needs to be released, because we can't just destroy energy, right? Energy is neither created nor destroyed, is one of the laws of thermodynamics. It is changed to another form. So here what's going on is that the potential energy in these bonds, what we call the chemical potential energy of the reactants, is being turned into heat energy when the reaction happens, because the products have a lower chemical potential energy. So that difference in chemical potential energy is not destroyed, it's just transferred, it's converted to heat energy that's released by the reaction. That's why when we burn methane, the room gets warm, right? Because there's a flame, there's a fire, and that fire gives off heat energy. That heat energy in this particular case is equal to negative 890.3 kilojoules per mole. That means that if I burn 1 mole of methane, that reaction will release 890.3 kilojoules of energy. So the negative sign tells me it's released. Oh, Let's make that small again. So the negative sign tells me it's released. That's why it's an exothermic reaction. The 880.3 is the amount of energy that is released, kilojoules. So 880.3 kilojoules of energy is the amount of energy released. And then the mole tells me from where, right? From where? Of a mole of, in this case, methane being burned. So released, it's negative, it's exothermic. 880.3 kilojoules is the amount of energy being released. And then by what? By a mole of methane in this case. Or from where? From a mole of methane in this case. So that's the y-axis and the difference between the reactants and the products in an energy level diagram. Now, we did talk about one other thing, and that was the activation energy. You'll notice that the reactants and the products are connected by a line, but that line does not simply just go down, right? We're not going just straight down from the reactants to the products. That's because here, in this little hill, is what we call the activation energy, or EA. The reactants turn into the products, but they don't do so just because. Think of methane, right? If we have methane, natural gas, that methane does not simply just catch on fire without a reason. Usually that methane will need a spark, something like a match to catch fire. So that methane will always need some kind of activation energy, or in this case a match or something along those lines. That match is what provides the activation energy to the methane to convert to the products. If it wasn't for the fact that these reactants need a bit of energy to get over this energy hill, in order to get over the hill and then be able to go back down and create the products, then methane will constantly be burning. Methane wouldn't exist. It will constantly always be burning. It's because it needs activation energy in order to burn that reactions don't just always happen. They need a push, in this case a match or a spark. That spark provides the amount of energy, the activation energy, that we need in order for the products to be created. So we need to get it going. We need to break a few bonds, which takes a bit of energy, in order for the reaction to get going and create the products. So this is what the energy level diagram, or the reaction pathway diagram, looks like for an exothermic reaction that gives off heat with a negative delta H. But what does it look like for an endothermic reaction? Now, for an endothermic reaction pathway diagram, or an endothermic reaction energy level diagram, the general aspects of these are the same. The y-axis is still the enthalpy change, the x-axis is still the reaction pathway, and we still have reactants on the left and products on the right. Now, in this particular case, we have calcium carbonate decomposing into calcium oxide and carbon dioxide. So I'm going to show this here. So we have calcium carbonate, CaCO3, which decomposes when heated, which is a key indication that this is endothermic. It's when heated, to give calcium oxide and carbon dioxide. So this being a reaction that requires heating to happen, that's a pretty clear indication that the reaction is endothermic. Now, notice how in this reaction, an endothermic reaction, the reactants are lower in energy in the y-axis than the products are. Now, we don't care by how much, right? We're not going to measure the distance from here to here because this is a sketch, not a graph. Now, but we can see that the calcium carbonate is lower, the reactants are lower than the products. That's a key indication this is an endothermic reaction. So to know with the endothermic reaction, we draw an arrow from the level of the reactants up to the level of the products, with delta H being positive. Positive in this case, 572 kilojoules per mole. Now what this tells us, the positive tells us that this is energy being absorbed, Therefore, why this reaction needs to be heated. 572 kilojoules is how much energy is absorbed. And then the mole again tells us from what? Or what is doing the absorbing. In this case, for every 1 mole of CaCO3 that is decomposed, 572 kilojoules need to be absorbed by the reaction for that to happen. So that's what this enthalpy change is telling us. It's telling us that for every 572 kilojoules that are absorbed, because this is positive, it's endothermic, 1 mole calcium carbonate will be decomposed. So that's what this number tells us. It's positive because the reactants are lower in energy than the products. We can see that because the arrow for the enthalpy change points up. Now again, we're going to have a hill connecting the products and the reactants, not a straight line. And that's because that hill coincides with the enthalpy change or the activation energy for this reaction. So the activation energy again is from the reactants to the top of that hill, from the reactants to the highest energy state in the energy level diagram or reaction pathway diagram. And that's the amount of energy that needs to be overcome. So in order for this reaction to happen, this calcium carbonate needs to be given enough energy to get over this hill for then to then roll back down and create the products, the calcium oxide and the carbon dioxide. So this activation energy, the distance from the reactants, not to the products, but all the way up to the hill, notice how it's positive, it's pointing up, is the amount of energy needed for this calcium carbonate to then automatically kind of turn into the products. So notice a much higher activation energy than the exothermic reaction, because this reaction requires constant heating, constant input of energy for the reaction to happen. So this is the endothermic reaction pathway diagram, and it tells us different things. So just to recap, regardless of whether it's exothermic or endothermic, we are going to have our reactants on the left side, our products on the right, and then whether it's endothermic or exothermic will tell us whether the products are higher in endothermic than the reactants or lower in an endothermic reaction than the reactants. But then connecting the reactants and the products, we will have that hill that is representative of the activation energy. The activation energy is from the reactants up to the top of the hill. And again, that's whether it's endothermic or exothermic, from the reactants up to the hill. And then the enthalpy change will be the distance from the reactants to the products. If it's positive, if the arrow points up, that positive enthalpy change means that we have an endothermic reaction. If the arrow points down from the reactants to the products, that means the enthalpy change is negative, meaning the reaction is exothermic because the products are lower in energy than the reactants. So let's look at a Cambridge question for this type of drawing. This is a question from a paper from a few years ago. We have sulfur dichloride is forming the following reaction. So we have S2Cl2 liquid reacts with Cl2 gas to form 2 SCl2 liquid moles. The enthalpy change of this reaction is negative 40.6 kilojoules per mole. And then the question says complete and fully label the reaction pathway diagram for the reaction between S2Cl2 and Cl2. Include labels for activation energy and the enthalpy change of the forward reaction. So what they're telling us here is that we need to draw and complete a fully labeled reaction pathway diagram, emphasis on fully labeled, and we need to include two things here. We need to include the activation energy, EA, and we need to include the enthalpy change for the forward reaction. And why is there forward reaction? We'll talk about the difference between a forward and a reverse reaction in a later chapter when we do equilibrium. But it just means of the reaction itself. Now, what we can get from the information they have given us is actually very important, because up here we see, oops, let me make that smaller. Up here, we see we have delta H is equal to negative 40.6. That negative means we have an exothermic reaction. And that's very important because, as we saw earlier, there's a difference between an exothermic and an endothermic reaction. In an exothermic reaction, the products are going to be lower than the reactants, whereas in an endothermic reaction, the products are higher than the reactants. So that gives us our first clue, because we need to finish. When they're giving us half of this kind of shape, we need to finish the rest of the shape. Because it's an exothermic reaction, the products, when we draw them, have to be lower than the reactants are, because otherwise this will be an endothermic reaction. So we're going to continue our line here and go down to a lower level than the reactants. Now, when we write the products, so we're not just going to write the word product, we're going to write 2SCl2 liquid, because that's our actual reactants, our actual products. This is for an actual reaction, so we need to include that reaction in our drawing. Now, we need to also include the activation energy. Remember, the activation energy is the distance from the reactants to the hill. So in this drawing, we need to draw the activation energy, which is the distance from our reactants in the y-axis up to our hill. And it says fully labeled, meaning when we draw that arrow, we need to put here EA to show that it's representing the activation energy. Finally, the other thing that we need to draw is the enthalpy change. Now, we know the enthalpy change is negative, so we know it has to point down. But where is the enthalpy change for the reaction? The enthalpy change is always going to be the distance from the reactants, and it's always from the reactants to the products. So here, in this particular case, we have our products here, they're lower, so from the reactants down to the products, that's our delta H, which in this case is negative 40.6 kilojoules per mole. And so now we have our labels. We have the label for activation energy. We have the label for the enthalpy change, which is negative, so it points down. Notice activation energy is positive because it's absorbed. The enthalpy change is negative, goes down because it's released. This is an exothermic reaction. And then we have finished that shape of the activation, the reaction pathway diagram, the energy level diagram, with the appropriate products. Not just products, but the actual products for this reaction. And this is, again, a sketch. Notice that we never plotted any data. We never did a line of best fit. This is a sketch of the activation energy. Could I have put these products a little lower? I could have. It doesn't matter as long as they're clearly lower than the reactants, because that's what we're showing. We're showing that the products are lower than the reactants. As long as that's clearly visible, it doesn't matter if I put them a little lower, a little higher, as long as it's clearly visible. Now, what I wouldn't want to do, I would not want to put those here, because then they're not clearly lower. It's in the same level. I wouldn't even want to put them here, because that's too close to the reactants. I want the change to be noticeable. All right. So if we look at the mark scheme here, you'll see that we have our rest of that shape of the energy level diagram. We have our products SCl2 here. We didn't need the state of matter, but doesn't matter. We didn't really need the coefficient, but again, doesn't matter. If we can include it, it's positive grading as long as we have the SCl2 here. It's fine. And then the activation energy is from the reactants up to the hill, and we have a label as EA. The enthalpy changes from the products, from the reactants down to the products. Again, we have that label as delta H. I added a negative 40.6. Again, didn't need to, but that's fine. And so what are the 2 points for? Because this is a 2-point question, or a 2-mark question here. The first is for the profile for the exothermic reaction, meaning that I completed this shape and that the products are lower in energy than the reactants. And then the other point is for me identifying the delta H and the EA with these 2 arrow and labels. All right. And that's going to give us the answer, the correct answer is going to be the shape and then the correct labeling, which is usually what it boils down to with sketches. Sketches are all about the shape and the labels. That is it for section 1 of chapter 6. We'll continue with section 2 in the next video. I'll see you all then.